Okay, so we have an f of x here, and we're going to bring to bear everything we know about intercepts, first derivative, second derivative analysis, and see how much we can learn about this shape. Now, this shape is a parabola, so we could graph this in pretty great detail without using any calculus, but let's use the calculus tools and see what they can do for us. Before we get into the derivatives, they ask about intercepts, and we can get those done fairly quickly. The x-intercept happens when y equals 0, which would mean 2x squared minus 9x minus 5 equals 0. If you factor that, I'm going to hustle this part a little bit. I believe it's 2x minus 1, x plus 5. 2x squared plus 10x, no, sorry. Let's try the other way. Two x squared minus 10x plus 1x, there we go. Okay, so x-intercepts would be from this piece, x equals 5. From this piece, we get negative 1/2. Those are our two x-intercepts. To save space, I'm just going to clear the work and put these at the very top. X-intercepts minus 1/2 and 5. The y-intercept is very quick. That's the one where x equals 0. If you put x equals 0 into this, you get 0 minus 0 minus 5. Done. Okay, so let's get a derivative. We'll start with the first derivative, of course, and see what that can tell us. Our first derivative, I'll use primes for this one, is 4x minus 9. And if we look for critical values of that, it's defined everywhere, but it's 0 when x equals 9/4, or 2.25. If we do a number line, which is a little bit overkill for a question this simple, but oh well. If x is smaller than 9/4, let's say it's 0, we get 0 minus 9, which is negative. If x is exactly 9/4, we get 0. If x is bigger than 9/4, let's say it's 1 trillion, we get 4 trillion minus 9, which is positive. Okay, so this confirms what we thought we knew about parabolae, that they go down and then they're flat and then they go up. So it looks like there ought to be a local minimum at this point, and its coordinates will be, the x will be 9/4, of course, and the y coordinate we get by taking 9/4 and putting it into here. Now, that involves some squaring of fractions and some common denominator stuff, and to keep this from going over 10 minutes, I'm going to just claim that the result is minus 121/8. So that is a local minimum. For a parabola, we also use the word vertex, and if you wanted to call it that, that would also be true. Now, so we have that our parabola is decreasing up to 9/4. It has a local minimum at 9/4, and then it's increasing after that. Those are our intervals of increase and decrease. Everything else we want to learn comes from the second derivative. And the second derivative is the derivative of 4x minus 9, which is, that was easy. The second derivative of a parabola is always a constant. That's one of the ways of defining them, actually. And so the second derivative is always positive 4, which means if you do a number line, it's pretty boring. It looks like this. The second derivative is positive always, which means this function is concave up always. And again, that squares with what we know about a parabola. If you were, this parabola always looks like a happy face, or if you were driving along it, you would always be turning left. Okay, so if we put all that together, how good of a graph can we do? X-intercept at minus 1/2. If that's 1, then minus 1/2 is there. Sorry, minus 1. And then here's x1, 2, 3, 4, 5, and we have an intercept there also. We have a y-intercept at minus 5. Ooh, did I give myself enough room? Just barely. No, I didn't, because that local minimum is going to kill me. I'm going to have to move this up. Okay, let's try this again. X-intercept at minus 1/2, x-intercept at 5, y-intercept at minus 5. We have a local minimum at minus 121/8, which is like minus 15.125. So the x-coordinate is 9/4, which is 2.25. And then we have to go down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'm fudging the distance a little bit just to try to keep this on the screen, but there is our local minimum, also known as our vertex. And you know what this shape is going to be, but if you refer to the first derivative, it confirms for you that the function should be decreasing until we get to 9/4, and it should be increasing after that, not a surprise. And this tells us it should be concave up, so curving in a happy face direction. So decreasing and concave up looks like this, increasing and concave up looks like this, and those are all things that we already knew about a parabola. So here's our graph. They didn't push us very hard with this first question, but we'll get increasingly complicated functions, and you'll find that with these derivative tools, we're able to tackle some very scary stuff that would have been impossible a couple weeks ago and get very detailed, accurate graphs. So we'll see you in the next one.